As an A-level physicist, you should know that there will be some form of synoptic assessment of your understanding. If you're doing Edexcel, this will come in paper 3. If you're lucky to be doing OCRA, all the exam papers will have bits of synoptic assessment. Indeed, all exam boards are required by Ofqual to provide elements of synoptic assessment. Students often find synoptic questions challenging and don't know how to prepare for them. The aim of this video is to help you realize that you can prepare effectively. First, I'll explain what synoptic assessment is, and we'll look at an example of a synoptic question. Second, we'll discuss the key change in mindset needed to rise to the challenge, namely, that you need to start viewing the specification as a network rather than linearly. I'll explain what all of this means in due course. Third, we'll go through concrete steps you can take to prepare, which includes trying papers from other exam boards and using powerful AI tools such as ChatGPT to generate practice questions. Along the way, we'll also touch on a few ideas and best practices from the cognitive sciences. The first thing you need to be clear about is what is synoptic assessment, or SA for short. A concise definition that I like can be found in the OCRA specification, which I'm going to quote. SA requires learners to make and use connections within and between different areas of physics. I've stressed the key to this definition, namely that in SA, students have to form connections between different parts of the specification to negotiate a question. So what might this look like in practice? Consider the following scenario. Let's say you're given a question involving a current carrying wire placed in a magnetic field, as shown. Since the current is DC, or direct current that flows in one direction, the wire experiences a downward force, as you can check via Fleming's left-hand rule. At present, this question would appear to be right at home in the magnetic fields part of the spec. But now suppose that the next part of the question introduces an AC, or alternating current that periodically reverses or alternates its direction of flow. This means that the force on the wire would also alternate upward and downward. You're then told that a segment of the wire is held in tension, given some extra info, and asked to explain why the segment undergoes large amplitude vibrations when the frequency of the AC is a certain value. The introduction of AC dramatically changes the nature of the question, bringing the topics of simple harmonic motion, SHM, and stationary waves into play. Thus, to tackle this question successfully, you would have to see and use the connections between these different areas of the spec, which might appear to be totally separate and unconnected. This scenario is based on a question from an AQA paper from 2011. I'll leave a link to the paper in the description and encourage you to have a go at it. Before we move on to the next section, let me point out that there are other forms of SA that you should prepare for. One form is mathematical in nature. Different areas of physics are often described by the same mathematical relationship, and so this essay tests your ability to apply relationships you've studied to unfamiliar situations. For instance, in year 13, you study exponential decay in the context of radioactivity and capacitors. But there are many other examples of exponential decay in physics, such as the manner in which objects cool down over time, and the decrease or attenuation of X-ray intensity with distance propagated through a material. In fact, X-ray attenuation is part of the OCRA spec. Another form of SA that you'll have to tackle is using practical principles to analyze unfamiliar experiments, along with analyzing and evaluating data from these experiments. In the interest of time, I'm not going to discuss these other forms of SA in this video. Let's move on to the second part of this video, where we'll discuss a key change in mindset that will help you get to grips with SA. You're familiar with your specification being laid out in a sequential or linear fashion, and we might call this a linear spec for short. The problem with a linear spec is that it suggests that the various topics, from mechanics to electricity and so on, are isolated from one another. A better way to view your specification especially to prepare for essay, is as a network spec. As shown, doing so enables you to see the connections between different topics. Notice that I've highlighted mechanics in red, since it's foundational and links to pretty much all other topics, and is therefore especially significant. Also, I'm not showing all possible links between topics, so what you're seeing here are the relatively obvious connections. Bear in mind though, that less obvious connections can exist between almost any two topics you care to pick. Remember the essay question from earlier that integrated magnetism, SHM, and stationary waves? The most important thing to take away from this is that topics aren't isolated, but rather connect with each other in sometimes surprising ways. SA tests your ability to see and use these connections. In other words, to see the forest for the trees. By the way, this network spec first appeared in a talk I recorded for an online conference, where I discussed the key importance of mechanics in A-level physics. I encourage you to check it out later if you'd like to gain a better appreciation of this. What steps can you take to prepare for SA? The first thing, the 0th step if you like, is to not delay and start as soon as possible. From experience, preparing for SA is time-consuming and uncomfortable at first, but it pays off in the long run. Doing so will not only improve your ability to deal with synoptic assessment, but should also lead to improvements in how you tackle all questions, synoptic or not. You may have heard of interleaving, the practice of mixing up your attention on topics rather than focusing on one exclusively and then moving on to the next. The latter is the traditional blocking approach, where you spend say an hour on topic A, then another hour on topic B, and so on. In contrast, in interleaving, you would divide your attention amongst say topics A, B, and C within each hour, either according to some fixed pattern or randomly. The research evidence suggests that once a threshold level of understanding is reached with topics, interleaving leads to better learning outcomes than blocking. Practicing synoptic questions, which naturally forces you to interleave, is therefore a win-win situation. You should use all available resources to prepare for essay, including checking out questions set by other exam boards. What you'll find is that questions sometimes reappear from one year and exam board to another, with variations. This isn't surprising. Question writers only have finite material to work with, and inevitably look at past questions from other exam boards to generate ideas and inspiration. Other useful resources are exam practice workbooks. For example, CGP have ones for AQA and OCRA, with sections on mixed questions, which are synoptic in nature. You may also want to check out Linking Concepts in Pre-University Physics by the Isaac Physics team at Cambridge, which is very cheap, although you can even attempt the questions online for free. While I don't have a copy, it's likely to be very good given that it's by Isaac Physics, with their emphasis on developing problem-solving skills. I'll provide a link to this book in the description. The key point is that by doing more synoptic practice, you'll develop a deeper understanding of how different areas connect and be less freaked out by essay. As you build up your memory bank of solved questions, you improve your chances of recognizing an exam question as something you've either already seen or being closely related to what you know. This sort of pattern matching is, in fact, one of the key tools we have for problem solving in any aspect of life. Now let's imagine, and you may need to really stretch your imagination for this, that you've worked through all past papers and workbooks and want even more synoptic practice. Where do you turn to? Powerful generative AI, such as OpenAI's ChatGPT models or Google's Gemini, can help you out. Such large language models, when prompted, can generate synoptic questions and answers. Let's take ChatGPT 3.5 for a spin and see what it cooks up for us. Of course, we first have to pick the topics or concepts we'd like to be combined in the question. Given the central importance of mechanics, let's pick a concept from there, say impulse, and prompt ChatGPT to combine it with a favorite topic of mine, SHM. Okay, so you can see that it's generated a question. Perhaps pause the video to read it. Overall, the question is coherent and appears similar to the style and scope of A-level physics. The bit in red seems to be an error in the compilation of LaTeX code. Don't worry about that. The impulse is 10 Newton seconds. The only part of the question that is a bit dodgy is the statement that the impulse is applied in the direction of motion of the particle. While impulse is a vector quantity, and therefore has a direction, the particle is initially at rest. Anyway, this is just a minor flaw. We can choose the impulse to act either left or right. Nothing that we're being asked to calculate depends on this choice. If you have time and are up for it, I encourage you to pause the video and try the questions before we take a look at ChatGPT's solutions. Alright, so how does ChatGPT reason about the first question? As you can read, it uses conservation of energy to figure out the amplitude of the SHM, setting the kinetic energy of the particle at equilibrium upon receiving the impulse to the elastic potential energy at maximum displacement. Recall that impulse is change in momentum, and so it's correctly calculated the speed of the particle upon receiving the impulse to be 20 meters per second. So far so good. However, upon plugging the numbers into the equation, it makes a surprisingly basic mistake on the left-hand side, which is a factor of 10 too small. It should read 100 equals 25a squared, so the amplitude should in fact be 2 meters. For part 2, calculation of the maximum speed, ChatGPT again uses energy conservation, along with the incorrect value of amplitude, to arrive at a maximum speed of 3.16 meters per second. Of course, this is nonsense. I point out that the maximum speed should just be 20 meters per second, to which it gives a pretty confused answer. As good experimental physicists, we should of course be doing repeats. I gave the same prompt 5 times to see the variety of questions generated. There wasn't a great deal of deviation amongst them. Some were simple variations on the question you saw. Others involved the oscillating mass colliding with, and thus imparting an impulse to, another stationary mass. Curiously, all the oscillating masses in the generated questions were half a kilogram. Given what we've seen, it's natural to be skeptical about the usefulness of large language models in practicing synoptic questions. AI models such as ChatGPT 3.5, while incredibly impressive and powerful, are far from perfect, and you should always be wary of their potential for flawed reasoning, including mistakes in basic arithmetic. Let me stress here that you should prioritize questions from past papers, workbooks, and so on before turning to AI. View using AI models as a bit of inspiration or a wild card in your essay prep. Despite the drawbacks, generative AI is useful for preparing for essay, and given the dizzying rate of progress, is only going to become ever more valuable in the future. One way of partially mitigating the flaws of ChatGPT and its rivals is by studying as part of a group, and double-checking the AI's answers and reasoning within the group. Group or social studying is generally beneficial for learning, and so this is an added bonus. As mentioned earlier, by doing more synoptic practice, you reduce the chance of being freaked out by a synoptic question. Some of my former tutees were shocked when I sent them a question combining SHM and impulse, which you can try for yourself and check your answer against my fully worked out solution. My tutees associated SHM with an oscillating pendulum or mass on a spring, and impulse with collisions, which is understandable, given that these were the contexts in which they first learnt SHM and impulse. Thus, they were shocked, because they couldn't see how these contexts could overlap. But SHM doesn't just describe the oscillations of pendular or masses on springs. It turns up in various scenarios from electric circuits to electric fields, to AC carrying wires in magnetic fields, as we saw earlier in the video. Similarly, the concept of impulse isn't just relevant to collisions. Impulse is defined as change in momentum, so whenever a force acts on an object for some time, that object receives an impulse. A mass performing SHM is most definitely subject to a force, so you shouldn't be shocked that we can talk of the impulse received by the mass. Over time, As you consolidate your understanding of concepts and store them in long-term memory, the context in which you first learnt the concepts fade away. Eventually, only the essential meaning of SHM or impulse or whatever remains in your brain's neocortex. AI models can assist in this process, which makes them a valuable tool in your toolbox for synoptic prep. Thanks for your attention. I hope you found this video useful. Please don't forget to like and share the video and subscribe to the channel. I'd love to know how you found using various AI models for preparing for synoptic assessment, so please do let me know by leaving a comment. Until next time, take care, and I hope to speak to you soon.